buy thousands or hundreds of thousands of these sensors and actuators and spread them all around your physical space. There's pervasive communication, 4G, 5G, and so on, is available all the time, everywhere, and at sort of much more affordable pricing that we would have ever imagined. Thirdly, you have access to computation as well, right? So things like cloud computing and edge computing, these have made the cost per sort of flop or cost per compute unit extremely cheap and also accessible by anyone. You don't need to be in some top institution to get hold of the HPC quality computing. You can literally go to Azure or Amazon and rent it for a few dollars or a few hundred rupees per hour and get going. And lastly, one of the themes of this sort of workshop is the advent of analytics, ML, AI, and so on, which has sort of seen a reawakening over the last few years through some of these deep learning techniques. And partly it's also due to the availability of data. It's not like some of these techniques didn't exist at all, meaning we had neural networks around for decades together. But the fact that you have enormous sort of quanta of data, the big data as opposed to the small data that Jan mentioned, is really the reason why ML is flourishing the way it is right now. So we have been looking to see how IoT and some of these systems and methods could potentially be used for improving, helping cities become smarter and sustainable, right? So I'll talk about two projects that I've been involved in, and both are sort of ongoing projects, and where it's a multidisciplinary project, a large team of faculty. So a lot of this work is done by the entire team, not just by my group. But one of the more interesting problems that we have been looking at is the one of air quality. And in India, before COVID struck, one of the biggest themes was in terms of the poor air quality in many of our large cities, which was in a sense will continue to cause once COVID effects go away. It affects our health, it affects the physical space, it affects even the Taj Mahal and so on. So these are sort of serious issues, and it's even it affects the even renewable energy, because solar fields, if you have a lot of pollution, your solar panels are not going to get adequate incidence of the sun, and the efficiency is going to go down and so on. So air pollution has a broad-based effect, right, across all layers of the society and the systems. And it's a fairly challenging problem to solve in a sort of big and emerging economy like India, which has got a lot of population, a lot of emerging industries and so on. So you can't just wish it away. So the question is, how can we better get visibility into the problem and then start designing techniques for fixing the problem, right? And one of the sort of challenges has been the lack of data on pollution. We all sort of know that, well, pollution is bad, and we have even sort of in Delhi, which is the largest city by population in India and one of the most polluted cities in the world from air population perspective, you probably have on the order of a dozen or so of the air quality monitoring stations, right, which are of a reference grade quality, right? These are sort of have instruments that are rated by the EPA, Environmental Protection Agency of the US. So it's like sort of gold standard in terms of monitoring stations, but you only have a dozen of those. But it's not just a spatial distribution which is slow. It's also the temporal availability of data. So if you look at this, a few years back, there was a bright idea that our the city government over there had to alternate the vehicles that can ply on the streets. And one day of the week, you would only have odd numbered license plate vehicle, and the other day you would only have even numbered license plates. So effectively, you're trying to halve the number of vehicles that are out in the streets. But that's great, but did it actually work or not? And that's sort of the big mystery, because when some of our sort of fellow scientists went and looked at the data from these reference gate monitors, they actually found that a lot of data, but for half of the instruments, their uptime was literally just like 40%, right? Or the uptime was literally close to zero. So only about 40% of all potential data that's available was actually being recorded for various maintenance issues and sort of so on. On the other hand, one of the collaborators in this project, he was part of a sort of non-profit organization that was doing crowdsourced low-cost air quality monitoring, and those were up by for about 80% of the time, right? And this sort of shows that sometimes you don't. It's better to have a lot of something of lower quality that might get the job done compared to a few of high quality, and oftentimes if it's not going to be up and running, right? So that was sort of the genesis of this entire project, and right, and which is actually between multiple institutions within India and the US. IIT Kanpur is leading it. We have civil engineer Professor Sachin Tripathi from there leading that. IIT Bombay is involved, IISc, as well as Duke University from the US. And this project is called SATFM, supported by the Indo-US Foundation. And here we are looking at enabling a network of low-cost air quality monitoring stations connected through IoT technologies and with the use of analytics to sort of help come up with air quality data at the city scale that is usable from a scientific perspective and policy making perspective, right? And we are at around year 3 of this 5-year project. Like you say, we are looking at sensors, we are looking at IoT protocol, communication protocol, analytics, and so on across the entire spectrum. So I'll give you some experiences from the last sort of 2 years or so where we have had some of these field deployments going on. It is sort of the big picture of this entire architecture. You have these IoT sensors. Again, our research is not necessarily on the sensors. We use off-the-shelf commodity-grade sensors that are relatively cheap, but obviously they come with downsides of poor accuracy and precision as well. But these are essentially connected through certain low-power ad hoc networks, like 6 or so panels what we are using. And in some cases where you don't have a lot of density of deployments, you might use 2G or 3G as well. And these are connected through Raspberry Pi gateway devices to the internet backbone. And then you sort of collect data, sample data continuously every minute or so, and push that off to the cloud, where you can really do various analytics, dashboarding, share it with the citizens, share it with the city managers, scientists, and so on, and take action, right? And the goal eventually at the end of 5 years is to actually have a city scale deployment of hundreds of these sensors that are up and running and sort of informing the public and policymakers. And this is sort of a view of something closer to the edge and the sensors. We have these air quality, which include both gas sensors as well as particulate matter sensors. We're focusing on NO2 and O3. These sort of sample sort of the pollutants continuously, gas and particle pollutants. And they use a wireless sensor network to sort of using a mesh kind of network to pass data to a Raspberry Pi device. We have some kind of resiliency and so on built in over there, so that even if the network is down or the Pi goes down, you can sort of revive data and push it off to the backend. And the backend is where some of the analytics take place. We also have some of these field deployments that have been going on for the past maybe year and a half or so. What you see over here on the left is the EPA rated gold standard sort of sensor. And many of our experiments have been around co-locating some of our own devices that we have put together alongside these reference gate monitors to see how the accuracy and sort of calibrations of these sensors that we are putting together can be improved upon. And just as a sort of to give you a sense of the cost, so the high-end sensors cost about more than $100,000 or so, while the ones that we are putting together, we are looking at around $200 or so, right? So we are looking at several orders of magnitude cost reduction. So the question is, instead of a single high-grade sensor, can you actually deploy 100 or 1,000 of these low-cost sensors to get much better sort of spatial coverage and potentially better temporal coverage as well, depending on the uptime and so on, right? So these are some of the sort of current setups that are there. This is sort of the latest edition of the box that we have going on. And this has evolved over time. So these are over the last 2.5 years. Our boxes have improved in capability, improved in terms of resiliency, packaging, form factor, and so on as well. And what's been happening in the last sort of 6 months or so, well, better part of the year if you discount COVID, is we've had these field deployments at the IIT Kanpur campus. We have about close to 40 or so of these sensors deployed at various parts of the campus, in various buildings, near hostels, and so on. These are sort of continuously collecting data. And alongside that, we also have these sort of lab grade experiments where we co-locate these sensors with the reference gate monitor to collect data. And we sort of do a live dashboarding and so on as a consequence of that. Right? And this is a sort of screenshot of data from a couple of months back that's being collected and sort of shown. Right? So now let's come to where the science problem lies. So that's all sort of the big picture context, right? So one of the key challenges with using these low-cost sensors is that the values that are reported from them are not necessarily accurate. Sometimes they can be fairly far away from reality, right? So what you see over here in the yellow line is a value reported in parts per billion for ozone by the reference gate monitor. And what you see in orange is the data reported by the sensors using the default calibration provided by the manufacturer of the sensor. In this case, Alpha Sensors, the manufacturer. And as you can see, these values are fairly far apart. Sometimes it's almost twice the reported value, and sometimes it's even going to negative values, which is sort of doesn't make sense. But this is what we actually get out of the from the manufacturer's calibration of the sensors. And obviously, this is not necessarily acceptable from a scientific perspective, and maybe even for policy making or decision making by individuals, it might not be acceptable. Right? I think the dotted line that you see over here is what is rated as the safe level of ozone for an extended period of time. And as you can see, these, while the yellow curve, most of the time it's within permissible level. It's only for certain days that it's exceeding. The orange line is mostly above that. So which means that you're getting a lot of false positives saying that it's unsafe while it's actually safe, right? So even from a gross approximation, such calibration is not adequate, let alone for scientific use. So one of the questions that we set out to try and answer is, can we improve the calibration of these low-cost sensors, right? And one way to think about it is this, right? So this calibration itself is applied on top of essentially these analog signals that you get from the sensors. These are electrochemical sensors. So effectively, you get the two different outputs from the sensor device for these gas sensors. And the calibration is nothing but coming up with a function that fits these two values into x1 and y1 into the actual parts per billion, which is what is useful for us, right? And this function f is something that by default the sensor manufacturer provides to you, and you sort of go ahead and use it, assuming that they have done their job, right? But obviously they aren't doing their job. Potentially the function cannot be generalized to just every part of the world. Maybe the conditions within India are not good enough, and the cities that we are deploying it aren't good enough. Or there might be other kinds of sort of ambient conditions that are affecting them that is not within the bounds of their calibration model from the manufacturers, right? So we essentially one way of thinking about this problem is that you want to predict y, which is the parts per billion, using these inputs, x1 and x2, that you actually get these raw signals that you get from the sensors. Right? That's the way in which you can model this. And again, at the end of the day, you want these models to be simple, because at the end of the day, scientists are not happy if you get a black box machine learning or a neural network model that says, trust my word for it, right? So that's what the prediction is. You want something that's explainable. And you also want it to be generalizable, right? So you don't want it to sort of go out of whack when you sort of swap sensors or swap locations. You don't want to go through a lot of data collection effort and sort of training effort and so on, because that sort of doesn't make it scale across different cities and over time. So this is sort of what the four calibration models we got from the manufacturer, and we sort of tried to use the best among them. And this is being shown for NO2, and the same thing is equivalent ones for O3 as well. What we the one sort of one thing that we did is start simple, right? Because at the end of the day, simple models that work are much better than complex models that work maybe incrementally better. So we start off with the simplest sort of quote unquote prediction model, a linear regression fit, and try to sort of incorporate additional characteristics such as temperature and humidity into this as well. And we also sort of tried out a regression tree model, which is again just a little bit of advancement over a linear regression, and tried out different permutations of that. So this is a screenshot of our regression tree model. And again, this was data collected from two different locations, from Mumbai and from Delhi, where we had some of our field deployments going on, co-located with a reference state monitor. And we sort of got certain results over a 7-week period and 10-week period in Mumbai and Delhi. And we sort of did some data cleaning, and sort of we report various values of maybe mean average, absolute error, RMSE, and R-square, and so on. Right? So quick summary of some of these results. All these A1 through A4 are the 4 different calibration models from AlphaSense, which is the manufacturer of the sensor. We have 4 different variants of the linear regression and 4 different variants of the regression tree model, right? And we are reporting sort of maybe R-square and so on for 2 NO2 sensors and 2 O3 sensors, right? And what we see is that across the board, if you just look at R-square for simplicity, right, you'll actually see that the R-square is fairly high for all 4 variants of the, regression tree model. And even the linear regression model is not too far away in relation to the R-square values, which are sort of terrible. And if you look at the percentage error, mean average percentage error, we are looking at the order of sort of 60 or 80% errors, and sometimes even sort of orders of magnitude off, while it's much more modest at 40% or so for the regression tree models. And in fact, NO3 is actually consistently performing worse than O3. And that's again some of the characteristics of the physics of the sensors and so on. So in general, for ozone, we are able to get within about 20% error or so compared to 100+% using the reference gate monitor. Right? So this was sort of a simple result, but a useful result, which showed that even with sort of basic techniques, you can go beyond what you get out of the box in terms of calibration. And you can sort of approach something that's scientifically usable, at least usable from a policy perspective out there, right? And just to sort of give you a visual perspective of this, what we earlier saw was the yellow and the orange line. Yellow is a reference state monitor, while the orange one was from the calibration from the manufacturer. Using our regression tree model and the linear regression model, you can see that they are approaching the yellow line, right? So oftentimes they are very close, and occasionally they might sort of deviate. But we are approaching a space where things are much more usable. And this is done at a 15-minute granularity in this particular example for ozone, right? Yeah, and we sort of tried it with different types of these are different models. These are violent plots for different scenarios that are being shown for Delhi, looking at the percentage errors. And we see that as the complexity of the model increases, at least for linear regression, you're able to sort of see a reduction in the error. But for the regression tree model, sort of tuning the happier parameter doesn't give you a dramatic difference. They're all around the same space. Obviously, as you sort of coarsen the time granularity, the error values decrease. So we did it at sampling granularities of 1 minute, 15 minute, and 60 minutes. You see that there is a sort of sharp drop between 1 minute and 15-minute granularity, but there isn't much of an improvement between a 15-minute and 1 hour, right? So the sweet spot seems to be sampling and sort of predicting or calibration at 15 minutes gives you a good balance between the granularity and the accuracy. And we also see some sensitivity to the location. So for example, Mumbai gives a much worse error compared to Delhi. And part of the reason we hypothesize is that Mumbai is a sort of coastal city where the humidity is very high, and Delhi is sort of almost like a arid region, like a desert, close to a desert region. And so spatial sort of sensitivity is definitely there. And here, our ongoing work is to see how much of transferability is there between models when you go across location. I'll have one slide. These are more recent results. We've been working with a machine learning data scientists more recently, a faculty at IIT Kanpur. And this is sort of an example of a glass half full versus half empty. So what you see over here are the comparison of the linear regression and the regression tree models against more sophisticated models. I don't claim to understand all of these more sort of complex models. Some of these are variants of the K nearest neighborhood models and so on. But these are not necessarily something that I would argue are explainable models, right? So what you see is that you do see improvement. So in the error, right? The y-axis is showing error as you go from some of the more simpler models to the more complicated models. And in fact, there's a separate plot which I'm not showing, which shows that in almost like 80 to 90% of the scenarios, the more complex model gives you a better result than the simpler model, right? But the question I come in, not as a data scientist, but just as a sort of general layperson or technical person, is that the magnitude of improvement is diminishing in nature, and it doesn't keep up with the complexity of the model, right? So that's to me a sort of takeaway. So that's to me the glass is sort of it's incrementally more than half full, but does it really matter, because the milk is not, or water is not really sort of interpretable, right? But that's again where maybe the domain scientists and the data scientists might disagree, or have different perspectives. And we also sort of have some work. All the results I showed you was from the context of gas sensors. We have similar work going on for particulate matter as well, where you see at this is IIT Kanpur for different weeks or different days of the month earlier on this year. And as you see, you can see that sort of there's a drop in the pollution level. And this is around the time that some of the lockdowns were getting enacted. So this is actually a sort of capture of the view of that, where you saw go from almost like 100 plus parts per billion to something that's approaching close to 20 or so, as sort of the COVID lockdown kicks into play. And this is from some of the field experiments that are currently going on, right? So again, there's a bunch of ongoing work, both from the ML side of things, but also from my own research, looking at how can you look at managing the life cycle of some of these models as you have a long-term deployment of these sensors on the field. You could sort of keep coming up with better and better models, but can you go back and say, hey, there is a result I got last month, which gave me so-and-so value, now it's different. Is the difference because the model has changed, or the actual ambient conditions have changed? So looking at sort of provenance, about the life cycle of models, life cycle of data, is an interesting problem. Also, how can you actually run some of these models, inferencing models, closer to the edge rather than sort of getting all the data back to the cloud? Is another question that my group was looking at. And also even in terms of how frequently do you train, where do you train it, and so on, are questions that we are trying to answer as we go along, right? So that's broadly in the context of the air quality monitoring project. So let me slightly switch gears and get into some work we've been looking at from an urban water management perspective. And here, again, water is probably one of the next big challenges that's probably much more pervasive across the world than even air pollution. And probably the next big conflict might be around not oil or energy, but water. Who knows? And one of the key challenges is in like developing countries like India. 24/7 water supply is not a given, right? So in fact, there are, I don't think there are any cities within India where you get 24/7 water supply from the city, right? Typically, the idea is that you would buffer water that flows in from the city into sort of overhead tanks or sort of sumps and so on, and that's really your source of 24-hour supply. And the city forgets to or doesn't have supply for a day or two, you might literally run out of water a couple of times a year, right? That's the reality. So we've been looking at ways in which you can address some of these challenges using IoT technologies. And recently, in the last year and a half or so, we've been particularly focused on inequity and safety of water distribution within urban cities, right? And earlier on, we had some sort of work within IISc campus, looking at the water management within campus, and that sort of led to this larger project that's currently being enacted within the Bangalore city. And Bangalore is, I think, the fourth or fifth largest city within India, 10 million plus residents. Oops, sorry again. And we are sort of looking at the southern part of Bangalore, which is about 20-25% of the population, which is split into about 83 different sort of units or distinct measurement units. And we want to sort of look at equity in supply, because a lot of the supply is sort of regulated. So who gets water, or which regions get water, is done in a little bit of an ad hoc manner, right? So if you look at this plot over here, what you see on the x-axis is are the different sort of neighborhoods, if you want to think of it, within Bangalore, within our region of interest. And what you see on the y-axis is the per capita consumption of water within that neighborhood, right? And as you can see, there's a wide range of variability in this or in these orange bars, right? So that's one thing, and this is also reflected in this shaded diagram, which tells you the lighter shades mean that the per capita consumption is low, while the dark blue regions mean that the per capita consumption is high, right? I think there are various reasons for that. Some of it might be because the physical systems over there, maybe it's in a slightly elevated region and the pumps can't push adequate water because of older equipment and so on. But it could also be social economic, right? So maybe the places that get a lot of water are the ones that have a very vocal population. There might be people who are who can pick up the phone and talk to the mayor or something like that if they don't get water, while the ones that are not getting adequate water are the ones who are sort of disenfranchised or sort of don't have as much of a voice, right? So again, the reasons could be several, but the question is, can technology play a role in making it more transparent, and also trying to come up with not ad hoc solutions, but very data-driven solutions or computational solutions that would normalize the sort of supply of water across the different regions to reduce the inequity. So some of the work that we've done, some of our team members have done, is to come up with different scoring functions for how do you measure inequity. Some of these are sort of known techniques that are applied to the water domain, such as the Gini index and Lorentz curve and so on. And we've also done some work in terms of how do you address this inequity through better pumping operations, right? So can you figure out which pumps, so if you've got a finite set of water available from various reservoirs that are supplying Bangalore, can you sort of figure out the pumping operations in a manner such that the right neighborhoods get adequate water, even though the supply might be intermittent, but they get adequate water over a 24-hour period that meets their requirement and falls within a certain bounds when it comes to the cumulative supply on a per capita basis. More recently, in the last few months or so, we've been focusing on safety of water supply. And again, there are a bunch of reasons why safety might be compromised, partly because of old equipment, or if someone is sort of doing some road construction, the things are highly unregulated over here. You would have people digging through a street, and you could have a sort of pipe leak or a pipe burst that brings in contaminants and so on. So one of the questions is, and this sort of goes into a little bit along the same flavor as what Jan was talking in terms of sensor placement. So if you had a finite set of these water quality sensors that can detect contaminants, where do you place it within the water distribution network to ensure that you can sort of immediately take preventive measures, right? And here there are different metrics for what you want to optimize for, and some of the common metrics from literature are reducing the mean time to detection once some part of the network has a leak or has a contaminant that introduces it. How do you minimizing the population that are exposed to this particular contamination? So how quickly can you detect it before a lot of population are affected? And also looking at how is it possible even to detect a contaminant, depending on where you're placing the sensor. If you're in the leaf of the network and there is no sensor beyond the point of contamination, you might never even detect that, right? And one of the key novelties we are bringing over here is one is in terms of looking at this from a temporal network perspective, rather than just a static network. And part of the reason to look at it as a temporal network is that, like I said, in India, the water supply is not 24/7, right? So which means the edge weights where the waters are flowing in, or even the cumulative water accumulated in the network, is going to vary across time. So can you incorporate those parameters into your optimization, right? So I think this sort of goes to the comment that's there in the chat window right now. So let me briefly talk about the approach that we are taking. This is currently a work in progress, so these are sort of very fresh results in a sense. So one of the approaches that we're taking is that we sort of cluster the entire graph network into various sort of communities based on topological structure, right? So for example, we look for edges that sort of separate out sort of two very sort of distinct communities with a very low edge weight. So which means that the water supply is more or less localized. The water doesn't flow out of that community too much from a network topological perspective, right? And you sort of form as many communities as the number of sensors that you have available to deploy. Right? So that's step number one. Step number two, we actually use hydraulic water models that are already out there from literature to model the intermittent supply within these various clusters within the graph. And then we assign temporal weights to each of the edges within the cluster. So these weights are, for simplicity, we have hourly weights. So every hour we sort of have an estimate of how much water would flow based on the current pumping plan for the city. And then what we do is that we come up with scoring functions for various vertices in this network that tells you, that gives you an indication of the priority of this particular node. If you put a sensor over there, is it going to be improving your objective function in a certain way? And one of these sort of scoring functions that we have sort of identified that appears to be working fairly good is one called temporal receivability, which is essentially in a sort of loose form. It's essentially the cumulative water that flows through that particular node as a sum of all the upstream nodes that are present, or upstream that are flowing through the upstream edges in this particular cluster, right? So, for example, the receivability of I would actually be MV. It's going to be a summation of MV and R. That R is the reservoir and I is a leaf. And likewise, the receivability of J is going to be based on V and R, which are upstream, right? And again, this is done using sort of temporal measures as well. So this is going to be changing across time. So once we have this kind of temporal receivability as a scoring function, then we essentially go in and look for the ones that give you the highest receivability and use that as a measure for prioritizing placement of sensors at those particular locations. Right? And we had some sort of preliminary results of that when compared to some of the other topology-based strategies in literature, as well as some of the computational methods-based strategies. What you see in green is sort of the proposed metric, and Z1 through Z4 are the 4 different objective functions that are commonly used in literature. So if you are further down in this list, it means that you're doing good. So we have some sort of early simulation results on both a fine-grained network at JP Nagar, which is one of the neighborhoods within Bangalore, as well as looking at a more coarse-grained network that's sort of a larger part of Bangalore. We're looking at an order of about a few thousand or so edges and vertices in the case of Bangalore, and a few hundred of them within the JP Nagar neighborhood, right? And as we see in some of these strategies for Z1, we are definitely performing well. In Z2, we are competitive with some of the better techniques, though we are not the best. And likewise for Z3 also, we are competitive among some of the better techniques. And in Z4 also, we are performing well better than some of the other techniques. Right? And similar results are seen in the other neighborhoods as well. Again, this is something that we are still trying to see how we can tune this better. And one of the reasons why we are doing better we see is that because we are capturing the intermittent nature using a temporal metric rather than seeing it as a static graph. But we are still looking to see if there are ways to improve this further, right? So I'm going to sort of wrap up over here because we are running out of time, and I'm happy to take questions. But to summarize, IoT and AI these offer sort of arguably new solutions to interesting new problems in various domains, and smart cities are one of them. And there are a bunch of interesting problems with respect to computational techniques, systems techniques, as well as analytical methods with respect to scalability, reliability, and so on. And as we are seeing from this workshop, some of these techniques can very well be applied to other domains, though they might have their sort of roots in specific domains. So I'll acknowledge the immense contribution by the rest of my team members in my lab, the Dream Lab, as well as some of our collaborators at IIT Kanpur and at IISc, as well as our funding agencies. Thanks a lot, and I'm happy to take questions.
Thanks, Yogesh, for a very nice talk. The group is now open for questions. So if you have any questions, you can post the questions here in the chat window. I myself had a question, and that was to do with the costs that you were talking about of these sensors. So I was just curious how the sensors do pretty much the same job, but the cost of the two sensors are quite different. Is it because the analytics, for the low-cost sensors are done at a centralized level, or they are done at the sensor level. So you analyze and say what the CO2 or NO2 level is at the sensor place, or you get some analog data to a central server and then you analyze and say that
Right.
these are the
Right. So no, I think for these the cost is sort of strictly a function of the technology that's used for sensing, right? And I mean, like you see, the instrument, it's really for doing the sensing using the reference state monitor. The thing is like the size of a refrigerator, right? And there's a lot going on. I mean, I don't claim to sort of understand all the internals of that reference state monitor. While for the sort of low cost sensor, it's pretty much the equivalent of some kind of a chamber where you essentially are measuring the conductance between two electrodes within that chamber that's letting in the air, right? It's extremely simple physics when it comes to the low cost sensor, right? So that's the reason why the costs are dramatically different, right? So the question that we are trying to answer is that despite the low cost and sort of the sort of very poor sort of signal to noise ratio you're getting, can you use modeling techniques or analytical techniques to get more out of the data, right? And the simple thing is to sort of just do a fit against these two electrode values, but also incorporating additional ambient conditions, right? And down the line, there's also value in looking at a cluster of sensors in a certain neighborhood and trying to see if you can make use of information from one sensor with another sensor as well as you go along. And another big factor is also the longevity of the sensors, because one thing that's been reported is that over a period of time, over a year or so, some of these gas sensors degrade in their quality, right? Can you actually figure out at which threshold they're sort of beyond their prime and you should replace them? And can you even sort of evolve your models to change your calibration over time to account for the lifetime of the sensor itself, right? Some of these are the sort of open problems, right? And by centralizing data, we might be able to answer some of these questions better.
So there's a question here, which is how do you determine the optimal number of low-cost sensors, a priori, that are required for the problem at hand?
Right. So right now we don't quite know the answer to that, right? So the glib answer would be that how much money do you have, right? But from a scientific perspective, it's more about because it's not even clear, to be honest, what is the question that you're trying to answer, right? Because the number of sensors would be a function of, is it a sort of very fine-grained scientific question that you want, or is it just a policy question that might be more easily answered? That actually gets into both the acceptable accuracy of a single sensor, right, as well as the number of sensors that you would want, right? And some of these are, to be honest, very open problems, and we are still not there yet in terms of what those answers are.
There's another question from Peter, which is, are you using the anonymized data from apps available on the smartphones as part of your data gathering?
Right. So these two projects that I talked about, no, we are not doing that. In a sort of one of the earlier sort of crowdsourced model of this one that sort of was sort of the basis for this more recent work on air quality monitoring, they were essentially using data from DIY things. So essentially there was a blueprint that you could actually download and buy these sensors off the shelf, assemble it, and plug it into your computer and sort of have a software run that will send the data to the backend. But in this particular project, we are not using crowdsourced data. Within campus, this is a couple of years back, within the campus residence, we did have a pilot where we were looking at water quality monitoring using essentially these reagent strips, like these reagent strips that are used for actually checking the quality of water in fish tanks, right? So they actually give you a nice different range of chemicals that are present in water. And that we were actually using in a crowdsourced manner where people could dip it in their sort of household water that they get from the tap and take a picture of that using an app we gave. And that would sort of normalize the colors and tell you what the water quality was. So that's something that we've played around with, but not necessarily at scale and not as part of these current projects.
So there are a few more questions, but I think I'll take one more in cause of time. So one of the questions is, are these sensors, the low-cost sensors, off the shelf, or they are lab designed?
Hey, so these ones that we're using in our current project, they are off the shelf, meaning they just shipped from Alpha Sense is a major supplier of low-cost sensors around the world. So we just using theirs. But there is a sort of parallel effort at IISc through a different funded project where they're using MEMS technology to actually get better output, much lower cost. I mean, what we are talking about is in the order of maybe $100. They're talking about a $1 costing sensor. But there, it's still, the jury is still out in terms of the calibration accuracy and so on, because the early results that we've seen aren't as promising as we've seen for the sort of current sensors we are using. But it might just be a question of time and some fine tuning. And maybe a few years down the line, this might be a non-issue once they have fixed the, once they've perfected the technology.
So I think there are a few more questions, but maybe it's best if that can be taken offline, especially some of them require, I think, a little bit more explanation. So thanks a lot, Yogesh. It was a very informative talk, and especially, it's also new for me while we still are at IISc. So thanks again for taking your time and preparing these slides and giving this very nice talk.
Great. Thanks a lot for inviting me. And again, my email address is out here on the slide, so feel free to drop me a note, and I'm happy to answer the questions offline. Thanks a lot. Bye.
Thanks.